Diffusion models are no longer being optimized simply to run faster. They're learning where to spend computation, how to preserve uncertainty while planning, and how to improve their own outputs without giving up few-step generation. This week's results from the University of Maryland and Hugging Face, Peking University's hierarchical video reasoning work, and Tencent Hunyuan's MeanFlowNFT point to the same shift. Efficient generation is becoming adaptive, structured, and increasingly agentic. We'll see why cheap drafts can beat elaborate search, why video models benefit from tree-like memory, and how reinforcement learning can upgrade 4-step image and video generators. Let's explore the first paper, FlashBond Instant Drafts for Inference Timescaling in Diffusion Models. FlashBond, from researchers at the University of Maryland and Hugging Face, challenges the assumption that diffusion model inference time scaling should spend computation on frequent intermediate verification. The paper shows that wall clock measurement, including verifier overhead, can favor broad best-of-n exploration over methods such as BFS, DFS, and ZOS. Its proposed pipeline first generates many inexpensive drafts, using a per-model configuration combining timestep, truncation, layer skipping, and second-order activation proxies. Qwen2, 5, VL, 7B. Then applies pointwise pruning followed by targeted pairwise ELO comparisons, and only the selected draft receives full quality refinement. Across GenAI Bench, GenEval, and Unigen Bench, using WAN2, 1.1, 3B, WAN2, 1.14b, and Black Forest Labs' Flux, 1dev, FlashBond leads under fixed wall clock budgets, with gains reaching 8% AUC at larger model scales, on WAN2, 1.13b. The full method achieves a 3.33x ISO quality speedup over Bond, while its combination with reflection tuning raises AUC time from 0.46 to 0.62. Candidate diversity, measured with the Venn score over Dynov, 2 features, correlates with final quality at Pearson R equals 0.75. The same draft-guided selection idea also accelerates FlowGRPO post-training. FlashFlowGRPO reaches baseline performance in roughly 10x fewer gradient steps, using 16 cheap draft rollouts to select 8 full trajectories. Let's explore the second paper, Hierarchical Denoising for Multi-Step Visual Reasoning. Researchers from Peking University and the Hong Kong University of Science and Technology introduce HDR, or Hierarchical Denoising for Visual Reasoning, built on WAN225B TI2V. Instead of forcing streaming autoregressive diffusion to commit frame by frame, HDR organizes video latents into a 6-level tree. Coarse layers preserve uncertain global plans, while finer layers refine them into concrete visual states. Its SHAP, or Sparse Hierarchical Attention Pattern, restricts each token to local and parent-level contexts, enabling coarse-to-fine planning with sparse KV cache reuse rather than dense temporal attention. On a 370 video benchmark spanning maze navigation, Tower of Hanoi, one-line drawing, sliding puzzle, Sokoban, and water pouring, HDR raises overall success from 34.22 to 60.29, a 76.2% relative gain over causal forcing, while average progress reaches 89.56 from 76. Streaming latency is 0.7 seconds per latent, making HDR 54.2 times faster than bidirectional diffusion during streaming. The model is also data efficient. With only 2% of the training data, it retains 82.9% of its full data success score, versus 52% for bidirectional diffusion. Robot maze experiments and the HDR WAM adaptation to RoboDojo suggest that hierarchical visual planning can transfer to embodied interaction, although remaining failures involve late-stage geometry and state consistency drift. Let's explore the third paper, MeanFlowNFT bringing forward process RL to average velocity generators. MeanFlowNFT, from Tencent Hunyuan and the Hong Kong University of Science and Technology, is the first forward process reinforcement learning method designed for mean flow generators, which predict average velocity over time intervals rather than instantaneous velocity. Its key innovation is to derive an induced instantaneous velocity predictor from the mean flow identity, apply the likelihood-free diffusion NFT objective to that predictor, and retain MeanFlow's native few-step sampler for inference. Theoretically, the authors show that, under idealized conditions, the induced optimum recovers the reward-improved policy and transfers that improvement back to the average velocity generator. Using finite difference derivatives, a shared reference derivative, and the forward conditional velocity for stable updates, MeanFlowNFT is evaluated on stable diffusion 3, 5, medium, or SD3.5M, and WAN 2.1 on SD35M. The 4-step model achieves the best result on 6 of 8 metrics, including an image reward of 1.4504 and OCR score of 0.6534, while matching or exceeding several metrics from 40-step diffusion NFT with 10-fold fewer function evaluations. On video, 4-step MeanFlowNFT reaches a VBench score of 84.33 on WAN 2.113B, surpassing the 50-step Longcat Video RL score of 82.57, demonstrating that forward process RL can improve quality without sacrificing few-step generation efficiency. That's a wrap on today's AI paper highlights. Thanks for watching.